with diplomacy, how can you emulate having a human involved in your training data and still have tons and tons and tons of training data?
In a game like diplomacy, we've actually shown that we trained a bot without human data just by playing against itself, and we played it with real humans and it didn't do well. So fortunately, there is a website, webdiplomacy.net, where humans play this game, and we were able to get training data from that site. And so we are able to use that to get some indication of how humans play. Deep learning by itself is not enough. There's AI beyond just deep learning.
All right, Noam, welcome to the Super Data Science Podcast, the first ever live filmed episode of Super Data Science. It's wonderful to have you here. So you work at Facebook AI Research, which is recently renamed to Meta A.I. So what is Meta A.I. and how does it fit into the broader Meta organization?
Yeah, so Meta A.I. is the branch of Meta that's focused on AI, on just AI more broadly. AI applied to products, AI applied to things like the metaverse, and also fundamental AI research. And so the sub-organization of Meta A.I. that I'm in, Facebook AI Research, is focused on fundamental breakthroughs in AI, not necessarily directed at a specific product, but just trying to advance the state of the art more broadly.
Awesome. And so I know that it isn't uncommon in the big tech organizations to be funding AI research groups like this that are working on fundamental AI research. But what is the big picture idea there? Why are big tech companies doing that kind of thing?
Yeah, so the big picture is that these companies are thinking about the long term. They're not necessarily thinking about just 5 years ahead or 10 years ahead, but also 25, 50 years ahead. And by funding this fundamental AI research, there could be breakthroughs that can't be foreseen currently. And if they're the ones that are creating those breakthroughs and funding those breakthroughs, then they are able to capitalize on it quickly. And so by getting a lot of smart people in a room together and letting them do AI research, not just blue sky research, there are potential products 25 years down the line that could emerge that they couldn't have foreseen today.
It sounds like an incredible opportunity to work in a place like that. Prior to being at Meta, you were doing a computer science PhD at Carnegie Mellon University. And while you were there, you developed the first AI to defeat top humans at no-limit poker. So you had Libratus as one of your algorithms. It received the Marvin Minsky Medal for outstanding AI achievement. And then you also had a Pluribus algorithm that was the cover story on Science magazine. So we really do have a star among us here. And so could you tell us a bit about these algorithms, Libratus, Pluribus? How did you develop these, and what are the differences between the two models?
Yeah, so taking a step back, like poker AI has been a topic in the domain for decades. In fact, if you look at the original papers on game theory by John Nash, on Nash equilibria, the only application that he actually discusses in the papers is poker. Because it's really, it really is a challenging game theory problem. Now, research really had been going on since the 70s, since the 80s. I think it really took off after Deep Blue beat Garry Kasparov. People were looking at, well, what's the next game? We have these games that can play perfect, we have these AIs that can play perfect information games where both players know the exact state of the world. But poker is very different because you have access to hidden information that the other side doesn't have access to. So research, I'd say, started really intensely in the early 2000s. I started my PhD in 2012. At that point, the research had progressed, but there was still a long way to go to actually beating top humans in no-limit poker.
It's a really interesting time, 2012, to be starting a PhD, because that was around the time that deep learning started making a comeback. So was that something that you focused on a lot, and was it incorporating deep learning perhaps into these algorithms that made a big difference?
Well, actually, in Libratus and Pluribus, we didn't use any deep learning. And I think a lot of people, in 2017 in machine learning found that quite surprising. It seemed like every breakthrough was happening with deep learning these days. But actually, I think it really showed that deep learning by itself is not enough. You have to there's AI beyond just deep learning. And it's not necessarily like a choice between the two. I think that the techniques are actually quite complementary. And since Libratus and Pluribus, a lot of my research has been on how do you combine the game theoretic reinforcement learning techniques that we used in Libratus and Pluribus with deep learning techniques.
Nice. So tell us about the algorithms then. How were you able to achieve these results? What were people doing before you started working on poker playing AI? And then what did you add into it that all of a sudden allowed your approach to beat the best players in the world?
Yeah, so a lot of the early research was focused on like linear programming approaches, which worked pretty well, but only at small scales. And when you go from like a small scale poker game to an extremely large game like No Limit Texas Hold'em, where there's more states than atoms in the universe, then the linear programming techniques simply don't scale. And so gradually the research shifted towards more of a reinforcement learning approach, which is actually the same kind of technique that was used, for example, in AlphaGo and AlphaZero. But the reinforcement learning techniques used in AlphaGo and these perfect information game AIs don't work in imperfect information games because they don't understand that that there's hidden information. And I think the best way to explain it is like in a game like chess or Go, if there's a good move, it doesn't become less good the more you play it, right? If you're gonna open with the Sicilian defense, it doesn't become worse if you open with it 100% of the time compared to 10% of the time. But in poker, that's not true. If you're gonna bluff 100% of the time, that's a lot worse than bluffing 10% of the time. And so you have to understand not just which actions are good, but how to balance the actions to get the probabilities right. And so you need to expand on the reinforcement learning techniques that were used in perfect information games to accomplish that.
Nice. Do you want to tell us a little bit more about that? Does it involve game theory concepts?
Yeah. So game theory was, this is the key ingredient, I think, that really let us go from perfect information games to imperfect information games. So we use game theory concepts, in particular Nash equilibria, minimax equilibria, and the idea there is that in every game, every finite game, there is an optimal strategy where if everybody is playing that strategy, then no player can do better by deviating to a different strategy. So what this means in a two-player zero-sum game in particular is that in every two-player zero-sum game, there is an unbeatable strategy that if you play it, you are guaranteed an expectation to not lose no matter what your opponent does. And I think a lot of people find this surprising, but you can think about rock, paper, scissors, for example. The Nash equilibrium in rock, paper, scissors is to randomize equally between throwing rock, paper, and scissors with 1/3 probability each. Because if you do that, then no matter what your opponent does, you are not going to lose an expectation. Now that said, in rock, paper, scissors, you might not win an expectation also, but in a more complicated game like poker, what we find is that if you approximate the Nash equilibrium, your opponent is going to make mistakes, and in the long run, you're going to end up winning anyway. And I should say, if you talk to professional poker players, modern professional poker players, they approach the game the same way. They try to approximate this Nash equilibrium, what they call game theory optimal strategy, and wait for their opponent to make mistakes.
You play poker, Noam?
I got really into poker when I was a kid. In high school, a little bit in college. Not so much for the gambling aspect. I was actually never really played for high stakes, but I was really interested in the strategy of the game. I think this idea that there's an unbeatable strategy in poker, and that if you could find it, then you just make infinite money basically. I thought that was a pretty interesting concept.
Yeah, and would you say that you achieved that? That you found a machine that could perform perfectly?
Yeah, I mean, I myself was not a very good poker player, but I guess my hope was that I could make a machine that could do it, and I think we came pretty close to that. I think it's fair to say that it's unbeatable by humans now.
Yeah, it's an incredible achievement, and clearly has already won a lot of plaudits. Now you're taking some of the concepts that you had from No Limits Poker. So this idea of hidden information that isn't available like it is in Go or chess. So you're just like the cards are hidden away from an algorithm or from a human playing a game. You're now moving on to another game at Meta A.I. called Diplomacy, which similarly has hidden intentions, hidden information. Can you explain the game of Diplomacy to us?
Yeah, so what's interesting is that poker, two-player poker in particular, is a purely adversarial game. Whatever you win, the other person loses. When we went to six-player poker, we thought that going from 2 players to 6 players is going to be a very difficult challenge in poker because of the fact that it's not 2 players zero-sum anymore. And a lot of the game theory concepts that we relied on don't carry over to more than 2 players. So for example, this idea that Nash equilibrium means you're not going to lose an expectation no matter what your opponent does, that really only applies in 2-player zero-sum games.
Oh.
And when you go to more than 2 players, you could lose and there's nothing you can do to stop that. I mean, if all of your opponents team up against you, there's no perfect strategy that's going to guarantee that you win. Now, it turns out that 6-player poker, this wasn't a problem. We used similar techniques. We added a lot of innovations to make it scalable. I mean, 6-player poker is obviously a much more complicated game than 2-player poker. And so we had to come up with new techniques to allow us to scale to that size. But this game theory problem actually ended up not being an issue. And that's because 6-player poker is a very adversarial game. There's no real room for collaboration among your opponents to allow them to team up against you.
Right.
But when you go to diplomacy, so diplomacy is this 7-player game where there is a big emphasis on cooperation in addition to competition. So the way the game works, it's kind of like Risk, if you've ever played Risk before. You control one of 7 powers, and you move pieces on a board, and you try to control, you try to take over the board.
It's like a map of Europe, right?
Yes.
Just like Risk.
Yeah. But the focus of the game is on negotiations with the other players. So at the start of each turn, you spend about 15 minutes talking to other players in private, negotiating with them, saying, I'll support you, I'll help you this turn if you help me next turn, or make all sorts of deals and alliances. But then at the end of that negotiation phase, everybody writes down their moves at the same time, and all the moves are executed simultaneously.
So when you play this in person with people, you would go off into separate rooms and that kind of thing. And so you'd kind of have this sense of like, you might have some sense of who's strategizing with whom based on who went off together and had a secret conversation, that kind of thing.
That's right. Yeah. So you don't know what the conversations that they're having are, but this person's talking to this person, and they tell you what their conversation was about. Maybe they're lying, maybe they're telling the truth. So there's a lot of intrigue. And then because all the moves are written down simultaneously, and because you're not held to any agreements that you said, there's a lot of backstabbing and betrayal that happens in the game. You tell somebody, or they tell you that they're going to support you, and then the moves happen, and you see, oh, they actually decided to attack you. And so it's a very different game from these purely adversarial games like poker, chess, Go. You really have to understand cooperation and trust, and be able to build trust with these other players, and understand the human psychology of the game as well.
That sounds incredibly complex to work into an algorithm today. This episode is brought to you by Super Data Science, our online membership platform for learning data science at any level. Yes, the platform is called Super Data Science. It's the namesake of this very podcast. In the platform, you'll discover all of our 50+ courses, which together provide over 300 hours of content, with new courses being added on average once per month. All of that and more you get as part of your membership at Super Data Science. So don't hold off, sign up today at www.superdatascience.com. Secure your membership and take your data science skills to the next level.
Yeah, and to be honest, like the reason why we decided to work on diplomacy next is because after poker, we saw the breakthroughs that were happening in games like Go, poker, even games like StarCraft, and it became clear that AI was advancing very rapidly. In 2016, you have AIs beating top humans in the game of Go. 2017, poker. After that, people were saying, well, StarCraft and real-time strategy games are the next grand challenge for AI. But that fell within 2 years. And so we wanted to say, we were saying, like, look, Go took decades for AIs to beat humans at. Chess took decades, poker took decades. What is a game that would be so beyond the capabilities of AI techniques today that it would take a similar amount of time? It would be similarly impressive if we were to succeed. And we felt like diplomacy was that game.
Yeah, that's so cool. And so there's 2 different variations on this diplomacy gameplay. There's the press version and the no press version, right? And so it sounds like the no press version could be easier because there's less communication, or yeah.
So we took on this really ambitious goal of making an AI that could beat top humans in this game. Obviously, that's a very long-term goal, and so as a short-term objective, we decided to focus on a simpler version of the game that's still popular among humans, where there's no explicit communication between the players during each phase.
Got it.
Now, this is still actually a very difficult challenge because you have to, so everybody just writes down their moves without talking to each other, and then they're executed simultaneously. But what's different here is because it's not a 2-player zero-sum game, you have to model the other players, and that's actually a key part of this game. You can't just approximate an equilibrium in the same way that you do with Go and poker and expect to do well, because you have to be able to model the other players and best respond to that. From a game theory standpoint, what's going on here is that there are multiple Nash equilibria. Like Nash equilibrium is this like really nice solution concept. In two-player zero-sum games, you can compute any sort of equilibrium, and they're all kind of interchangeable. You don't have to play the same one as the other person in order to do well. But in a game like Diplomacy, there are multiple different equilibria. And so you could, through self-play, just by learning from scratch, playing against yourself, learn an equilibrium, but it doesn't mean that you're going to do well with actual humans because they might be playing a different equilibrium. It's kind of like with self-driving cars. If you had a car that learned to drive purely on its own without any human data, it might learn to drive on the left side of the road. And that's a totally reasonable solution. It's an equilibrium that's totally valid. But if you were to put it on the roads in Manhattan, it would not do very well. So you have to understand how humans drive and how humans play these games in order for the AI to do well in these games.
So that presents to me perhaps one of the big challenges here is where do you get your training data for something like this? So the contemporary Go game playing algorithms, while they originally, so AlphaGo, the one that's popularized in the AlphaGo documentary, was trained on some human gameplay. But then the more recent versions of the game, there's no human gameplay that it's trained on at all. So you just have the algorithm playing against itself, and in so doing, it comes up with ways of learning and ways of playing Go that had world champion Go players describing it as like having aliens on Earth. So with Diplomacy, how can you emulate having a human involved in your training data and still have tons and tons and tons of training data?
Yeah, so that's right. So AlphaGo did use human data, but the more recent versions, AlphaZero, don't use human data. You don't need human data to do well in a game like Go. And actually with poker as well, we didn't use any human data, and we were able to beat top humans. And that is a feature of purely adversarial games. But in a game like Diplomacy, we've actually shown that we trained a bot without human data just by playing against itself, and we played it with real humans and it didn't do well. So fortunately, there is a website, webdiplomacy.net, where humans play this game, and we were able to get training data from that site. And so we are able to use that to get some indication of how humans play. It's not a huge amount of data, but it is enough that we were able to build a bot, that we were able to model the humans and then build a bot that could play well with that human model.
Oh, wow. So, and then that bot, is it using the same kind of deep reinforcement learning that you're using for the general Diplomacy algorithm that you're building, or is it some kind of separate algorithm?
So what we did is this is actually very cutting edge research. So we actually just put out a paper recently on this, and we're going to put out another paper in the near future going into more detail about this. But like so I should start by saying how the Go and poker AIs work. They start from scratch, playing totally randomly, and then play against themselves. And in that process, so what's called self-play, they gradually improve. So they understand, okay, this action's making me more money or winning more often. I should take this more often in the future. And in the long term, they eventually converge to this equilibrium. And in Diplomacy, we end up doing something similar, except we regularize the algorithm, we regularize the policy towards this human imitation learning policy that we have. So we regularize it towards the human data. And so in that way, it's finding an equilibrium that is in some sense compatible with how humans are playing. And so we actually ran a competition just recently where we pitted this AI against 50 real humans, more than 50 actually, quite a few real humans in a tournament. And the AI came in first place in no press Diplomacy.
Wow, and so that's what you just published on.
That is actually still, it's going to be published soon, but the technique that we described in an earlier paper and this result we're going to publish in the near future.
Incredible. So are you able to go into any more particular detail on the deep reinforcement learning approaches that are involved in having the algorithm work so effectively in order to be able to beat humans at the no press version? So it's the no press version of Diplomacy. You now just have hot off the press this result that you can beat them. And so how does that work? Tell us in detail about the deep reinforcement learning technique involved.
Yeah, it's actually in some ways similar to the AIs that are used in poker and Go and chess, other than the fact that we're regularizing towards the human data. Now, one thing I should emphasize, and I think is underappreciated in the wider AI community, is that aside from this wasn't just model-free reinforcement learning that we were using. It actually a big focus of the research was on search. So instead of the bot just acting instantaneously, when it's turn to act, it will actually compute an improved policy for all the players. It will try to figure out what is the optimal policy for all of the players on this turn, given my value function about what's going to happen after this turn, the values to all the players after this turn. And this is actually similar to what's done in Go and also in poker. AlphaZero, AlphaGo, they use Monte Carlo tree search. And that is a critical component to reaching superhuman performance in Go. In poker also, the big breakthrough that allowed us to beat top humans compared to prior bots is that we added search. So on each turn, it was figuring out its optimal policy for the entire round of poker that it was on. And this is actually done in a tabular way. It's not done using neural net function approximation.
All right.
But it is using neural nets to predict the value at the end of the turn. So it's using an estimate from the deep neural nets to predict the value at the, beyond this turn, and then based on that information, it's computing the optimal policy within the turn.
Nice, super cool. So how are projects like this potentially relevant to real-world applications? Actually, even before we go to that, now that you've succeeded at beating human players at no press diplomacy, the big research question is going to turn to press diplomacy, I imagine, which is going to be presumably orders of magnitude more challenging, because once you can have natural language communication, the kind of behind the scenes strategizing and lying, in order to have a machine that could perform well at that, it would have to have a deep understanding of natural language and human behavior in the context of lying and strategizing. It sounds like a big jump to have to do that.
Yeah, so like I said, I see this as a very long-term research agenda, and I think by making an expert level no press diplomacy bot, we've just done the first step of maybe a dozen steps. We don't have to jump straight to natural language. There are ways that you could, for example, allow bots to communicate without with a small communication channel where they're just sending a few bits back and forth. There's a lot that we can do, and I think there's a lot of interesting research questions that come up even in that domain. But yes, the long-term goal is, can we get this bot to play in natural language with humans and do well? And I think if we can get there, I think that the applications I think are pretty clear.
Yeah. Do you have a few examples?
Right. Well, I mean, I think first of all, just with the no press diplomacy, I think we've had really fascinating breakthroughs with being able to model humans. And I should say also, we're doing experiments now to see if this technique is more broadly applicable. And we found that similar techniques work well in Go for modeling humans. It works well in Hanabi, another cooperative card game for modeling humans. And I think there's potential for this to more broadly be used to model human behavior in the real world. And that's ultimately the goal. I mean, we're not here to just make AIs to play games. We're here to use games as a benchmark to measure progress against real humans, but to eventually apply it to the real world. And so I think by being able to model humans better in these games, we can use these techniques to better model humans in the real world and develop AIs that can collaborate with humans in the real world as well. So for example, I think one clear application might be self-driving cars. The big challenge with self-driving cars is modeling the behavior of other humans on the road. You can't just assume that they're going to behave the same way that the robot's going to behave. And like I said, there's all these different conventions, quirks that humans have that you have to be able to understand, even if they're irrational. And that's what we're able to do in diplomacy, and hopefully those techniques extend to these kinds of domains as well.
Amazing. Exciting to see what continues to come out of your research group. And so speaking of doing research at Meta A.I, you were a very accomplished PhD student, award-winning models, featured on the cover of magazines. You probably had your pick of companies that you'd like to work at or academic institutions that you'd like to work at. So why did you choose to do research at big tech, at a big tech company, specifically Meta AI, instead of staying in academia?
Yeah, that's a good question. So actually, my original plan was to go to academia, to become a professor. And I planned to do just a 1 year in industry research in between grad school and starting as faculty member. And so I did interviews for the big tech companies, and I got the offer from Meta AI, from Meta, previously Facebook, and they said I could start immediately instead of waiting until after I graduated. And so I told them, like, look, I'm going to be going on the faculty market. I'm going to be interviewing with universities for like 3 months, just flying around the country, not doing any work for you all. And they said, yeah, that's fine. Just come here. We'll pay you to do all that, and no big deal. And so, I thought, okay, well, that's strictly better than being a grad student, making $35,000 a year. So why not, just join Meta? And so I did, and I was there for about 6 months. I did all the faculty interviews. I had some really great offers that I was really excited about. But at that point, I had gotten to see what it's like doing research in Meta, and I thought it was amazing. I thought it was simply a better opportunity than being in academia. My collaborators were top-notch. I had complete freedom to pursue any research that I wanted to. We had access to more resources. And so, in pretty much every way, it was an advantage over being a professor. I still, consider, I think what really did it for me is I was talking to a professor on a second visit about my choice between going into industry research or going to academia. And this professor had actually been at AT&T Labs in the early 2000s. And what he told me is, one of the big risks of being an industry research lab is that they might go away. And with faculty, you have tenure. But he told me, look, when AT&T Bell Labs, kind of went under, it kind of shifted away from long-term research to more short-term research, and a lot of the prominent researchers left. They all got great jobs in universities. And that made me realize that it's not like I have to choose right now between those two paths. I can always go from industry research into academia later. And so for me, I decided, look, this is the better opportunity right now. I'm able to do my best research here. So I'm going to go with Meta.
Amazing. Makes a lot of sense. And I can definitely see why you chose to do that. So I do have a couple final questions for you that I'll get to later that are my standard questions that I end episodes with. But in the meantime, I thought I'd open it up. For the first time ever, we can have people in the audience ask questions from the guest on Super Data Science. And so I wanted to open up the floor to that. So we do have a mic that we can pass around. And as you do that, it would be awesome. You can let us know maybe your first name and what you do, and then ask your question.
Yeah, so the question was, what are the main barriers to getting these techniques beyond games to real-world applications like self-driving cars? I think the main challenge is that in a game you have well-defined environments with well-defined payoffs. You either win or you lose, and you have a choice between a finite number of actions. And in the real world, things are not so clear. It's not really clear what happens after you turn the steering wheel right. I mean, you kind of have an indication, but it's kind of unpredictable. And then also, like, what's the objective function that you're trying to maximize? That's also a bit more fuzzy. And so things are just less well-defined in real world compared to in a game where you know exactly the dynamics model. Now, there has been a lot of research on overcoming this. And in fact, I think one of the research breakthroughs that I was really excited about is MuZero. This is a new technique out of DeepMind as of a couple years ago. And it's like AlphaZero. It's able to play Go at the same performance as AlphaZero, except it doesn't know the rules of the game. It's learning the rules as it goes. And that is, I think, a big step towards applying these techniques to the real world. And I think if a lot of researchers are pushing in this direction, and I think the research that we're doing on cooperative games and imperfect information games can be extended to the real world once there's more breakthroughs in that kind of research. Yeah, that's a great question. And this is definitely true that when you're driving on the road, you have to understand, other participants are not going to behave the same way that you are. And obviously we're not doing this on roads yet. We're focusing on games, but yeah, also with humans in these games, there is a style that humans have, and you have to be able to adapt to that kind of style. And so if we have data, and I think that's the key, that we need to have data on how humans are behaving. And if we have that data, then we can model how they behave, and then we can respond to that appropriately.
Do you think that an algorithm would be able to identify when it's in a particular context? I guess so. That you're in Connecticut or Peru, and so that could be a parameter in the model, or yeah.
Yeah, and I think you could. I think if you have sufficient data, you should be able to pick up that where I am, who I'm driving with. You can see the kind of behavior that they're exhibiting, and you can, based on their previous behavior, you can kind of predict what they're going to do in the future. Yeah, so if you notice that they're driving like Peruvians, then you can predict that they're going to drive like Peruvians going forward, and other people on the road are going to drive like Peruvians. So the question was, how does the AI know when to bluff? And first of all, I should say, I think it's really smart that you do not become a professional poker player. They're not, with the breakthroughs in AI that are happening, it's not a very good profession to be in these days. In fact, a lot of, when we were doing this competition, we made this AI, we played it against these top professional poker players. And at the end of the competition, they were coming to me for career advice, because they are realizing like, our days are numbered as professional poker players. And I thought this was really bizarre, because like I'm this poor grad student, and these are like these high roller poker players, and they're coming to me for career advice. But yeah, fortunately, a lot of them were able to transition away from poker very successfully.
Couldn't you also, at least in online poker, there could be bots playing against you, but surely just like, you could have a Go computer that can be the world's best Go player. There's still some sport in watching humans play Go against each other. So you could presumably still have high-stakes poker games where no bots are allowed, no robots. Yeah,
so actually a lot of the really profitable poker players were playing online, because they were simply able to play more tables at the same time. And online poker is at a point where it's really difficult to play high-stakes poker because there's this risk of bots being on these websites. And so, there is still an active professional poker community, but a lot of it has shifted towards live poker, where there's less money to be made. Still, if you're really good, you can make a lot of money, but not talk about like the same order of magnitude that it was 10 years ago.
Nice. And then, did we answer your question?
No, we did not. So to answer the question was, how does the AI know when to bluff? So the bot actually learns this through self-play. I think a lot of people find this surprising, that the bot doesn't view bluffing as lying. It just views it as the action that makes it the most money. If it has a bad hand, it has a choice between folding or raising. And if it raises, it understands that there's a chance the other player might fold. And it learns this through experience, that it played in against itself in previous games, and it saw in those situations, if it raised, that player folded. And so it understands that if it does that, there's a good chance that it'll actually make money. Now it has to get the probabilities right. And so that's, I think, the big challenge. It has to understand that if it raises too much, and it learns this through experience as well, that if it starts to raise too much, too often, and then the other player starts to call instead of folding, because it understands that, this person, when they're raising, they don't actually have a good hand. I'm going to start calling more often. And so then, the bot that's bluffing will bluff less often. And so they kind of go back and forth, but they eventually arrive at this equilibrium where the bot is bluffing with the right frequency and the other bot is calling with the right probability, so that it all balances out.
Cool. There you go. Great question.
That's a great question. The question was, is the bot adapting to these players as the game goes on, like between hands? So for the Libratus and Pluribus, we actually did not do this. The bot was simply trying to approximate the equilibrium, and it wasn't trying to learn the human style and try to exploit them. And this is actually sufficient for beating top humans in poker. I think a lot of people found this surprising as well. But it's true that a lot of professional poker players take this approach as well. They just try to approximate the equilibrium, and they understand, like, look, I'm playing against somebody that is really strong. They're not going to have many weaknesses anyway. Let me just approximate the equilibrium and do well. Now, where this is a problem is, like, if you're playing against weak players, the bot is still going to do extremely well. It's still going to make a ton of money, but it might not make as much money as a top professional would that could exploit this weak player's weaknesses. Now, that said, with the recent research that we have in no-press diplomacy, we've developed techniques that allow you to balance playing in equilibrium with modeling the opponent and best responding to that. Now, in cooperative games, that is essential, but also in competitive games, it allows you to exploit the other player's weaknesses. And so one of the things we've considered doing is revisiting poker and seeing if we could develop bots that can, in addition to playing in equilibrium, also exploits the weaknesses of its opponent. Now, we're probably not going to go this route because I feel like poker is done and we have bigger fish to fry. And it's also quite difficult to get data for this. But it is something that I think is now possible and that has never been possible before with poker AIs.
Super cool.
Yeah, so the question was, for people that are interested in breaking into this field, are there any recommendations? So for me, I kind of went about it in a fairly roundabout way. So I actually started off in more of the game theory side. So I worked in computational game theory, and my plan was to pursue a PhD in computational game theory. Poker, the challenge of making a poker AI was considered a game theory challenge, and so that's why I worked on that. And gradually, my research shifted more towards the deep reinforcement learning side of things. I think if you want, I should say, breaking into these fields is very competitive these days, but there are opportunities, and I think a lot of it is that you have to be self-motivated to pursue these kinds of directions. Becoming familiar with machine learning concepts, becoming familiar with PyTorch, being able to demonstrate research aptitude. It doesn't have to be in a career that you're doing right now. It could be on your own, and in fact, in some ways, it's even better because it shows that you're really motivated. Then, if you want to become a research engineer, yeah, you just have to show strength in this area from an engineering standpoint. And if you want to become a research scientist, which is honestly not that different, you have to go for a PhD in one of these universities and work with somebody who does research in this field.
Nice. All right. Excellent questions. Thank you. We got one more? Okay, we got one last one.
So the question was on the interpretability of our techniques. Are we able to interpret what the bot is doing and why? And I'd say the answer is no for right now. It's not a priority for our research to be able to better understand the reasons why the bot is taking these kinds of choices. Now, that said, I think one of the interesting things about the human modeling aspect is that it actually makes it easier. So I think we were discussing earlier that with the state-of-the-art Go AIs, they play in a very alien style. It seems like Martians coming down and playing without ever having been exposed to the way humans play. One of the things we're able to do with these new techniques is that we're able to make really strong AIs that behave in fairly human-like ways. And so you can develop a Go AI that is really strong, and in fact is stronger than any human alive, but still plays in a fairly human-like style. And so in that way, it can actually be used to help humans get better at their game, because it's not like this is totally foreign for the human. It's just an improvement, a slight improvement on where they're at currently.
All right. So excellent audience questions. Thank you very much, everyone. We just got a couple to wrap up the episode. It's our usual questions that I always have. Noam, do you have a book recommendation for us?
Book recommendation. So I recently read, in preparation for working on diplomacy, Never Split the Difference, which I actually thought was a generally useful book, but I think it was also useful in particular for my research because it made me appreciate that a lot of negotiating and communicating, it's not just about behaving perfectly rationally. You really have to understand the human aspect of it as well. And I think for an AI to really succeed in these kinds of domains, it also has to understand the human elements, not just assuming everybody's like a robot.
Nice. So a negotiating tactics book was useful for you as a person as well as an AI researcher.
I'd say so. Yeah, I realized that everything, pretty much a lot of things in everyday life are negotiations. Maybe just not framed typically in that way. And so I thought it was a generally useful book.
And then one final question, Noam, is how do we stay up to date on your latest?
Yeah. So whenever we have a new paper out, it goes on Google Scholar, and so you're able to follow me on there. Also, I use Twitter. So my handle is Polynomial, Polynoamial. So it's kind of like a pun on my name.
Yep.
And I think those are the best ways.
Nice. We'll be sure to include that in the show notes for the episode. Thank you so much, everyone here live at MLConf in New York. It's been awesome to have this first ever live experience. Thank you for the people who were willing to whisper off in the sides. And yeah, thank you so much, Noam, for being here. A really incredible guest. We learned a ton from you, I'm sure.
Thank you for having me. It's been great.
Awesome. Thank you for joining us for that first ever episode of Super Data Science filmed in front of a live audience. Noam's eloquence and brilliance made what could have been a stressful experience a smashing success. In today's episode, Noam filled us in on how Meta invests heavily in its prestigious Meta A.I group in order to develop technology that could be dominant decades from now. He talked about his Libratus algorithm, which defeated leading professionals at two-player no-limit poker, his Pluribus algorithm, which defeated leading pros at multiplayer no-limit poker, how computational game theory is critical to allowing his algorithms to excel against humans, how Monte Carlo tree search combined with deep reinforcement learning enabled Noam and his Meta A.I colleagues to devise a model that could excel at no-press diplomacy, a complex strategy game wherein anticipating human intent is critical to success, and how breakthroughs in models that can anticipate human intent like these models could be a boon to practical applications like self-driving cars. As always, you can get all the show notes, including the transcript for this episode, the video recording, any materials mentioned on the show, the URLs for Noam's social media profiles, as well as my own social media profiles at superdatascience.com/569. That's superdatascience.com/569. If you enjoyed this episode, I'd greatly appreciate it if you left a review on your favorite podcasting app or on the Super Data Science YouTube channel. I also encourage you to let me know your thoughts on this unique live episode format directly by adding me on LinkedIn or Twitter, and then letting me know you thought about it. Your feedback is invaluable for helping us shape future episodes of the show and to determine whether we try to do things like filming in front of a live audience again. Thanks to my colleagues at Nebula for supporting me while I create content for you. And thanks, of course, to Ivana Siebert, Mario Pombo, Serge Massis, Sylvia Ogveng, and Kirill Eremenko on the Super Data Science team for managing, editing, researching, summarizing, and producing another trailblazing episode for us today. Keep on rocking it out there, folks, and I'm looking forward to enjoying another round of the Super Data Science podcast with you very soon.